Hello, in this presentation we're going to introduce Euler angles, one of the most common and most used representations in robotics to describe a 3D orientation. The aim of this presentation is to introduce the representation of Euler angles with its 12 variants. We are also going to see the concept of gimbal lock, as well as to know how to transform the orientation between Euler angles and rotation matrices that we saw in a previous video. Euler angles define a 3D orientation by using three angular coordinates, and with these three angular coordinates we have up to 12 different types of representations. The letters used in this representation, read from left to right, imply consecutive rotations on the mobile reference system. We can distinguish between a set of representations that apply a first and a last rotation on the same axis, known as proper Euler angles, and a set of representations that apply rotations on each of the axes, known as Tait-Bryan angles, also called nautical angles. When using Euler angle representation, a similar situation to a current suspension can occur. This is mechanism as shown in the figure, and this mechanism can get locked when two of the three axes of the rotation are placed in parallel, which causes a loss of degree of freedom, and therefore there is an axis on which we cannot rotate. In the case of Euler angles, we can see that two of the angles describe the same rotation. In fact, this can be clearly seen in the plane figure, the one on the right, where the outer and the inner magenta circles contribute to the same rotations when it's in the situation of the gimbal lock. To be more specific, we show here a representation of three consecutive rotations using Euler representation ZXZ. As I said, we need to understand these rotations read from left to right, the letters, and apply to the mobile reference frame. So it implies a rotation around Z axis, then a rotation around X axis, the mobile, so it's indeed U. And then we apply a final rotation around the Z-axis, which is the mobile frame again, which is W. Okay, so this implies three consecutive rotations, or the multiplication of three consecutive rotation matrices as shown in the slide, and because they are done in the mobile reference frame, they need to be post-multiplied, as we saw previously in the rotation matrices video. So this is the analytic expression in this case for this Euler angle representation, but since we said that we have different variants, we can also have, or we can see here in this other example, a different representation. In this case is ZYZ, so implies a rotation around Z, then around V, remember it's the mobile frame, and then a rotation around W, which is again the mobile frame. So this implies a post-multiplication of a rotation matrix around Z, post-multiplication of a rotation matrix around Y, and then finally another post-multiplication around Z again. In this other example, rotations are around the three axes, that is three different axes, that is around X, Y, and Z. This is in fact the representation that we will use in the Sim robot simulation software that is discussed in other video tutorials. And this is the analytic expression in order to convert the three angular coordinates into a rotation matrix. And finally, here we see another example of a rotation with Euler coordinates Z, Y, X. This representation is indeed equivalent to the roll-pitch-yaw angles, denoted by the letters RPY. This is a representation that is frequently used in nautical applications to describe the orientation of, for instance, drones or planes. To convert from a representation in Euler angles into a rotation matrix, we need to do the post-multiplication of sequential basic rotation matrices, as I indicated before. So depending on the specific representation, the rotation matrix will obtain a different symbolic expression. Here we show the symbolic expression for the representation XYZ. But on the contrary, if we intend to obtain Euler angles from a rotation matrix, then we have to take a look to the symbolic expressions of the actual representation of the rotation matrix in Euler angles. So if we observe the element 1, 3 of the rotation matrix, the one in red or highlighted in red, it's only affected by the beta coordinate of the Euler representation. So this means the arcsine of this number is indeed this coordinate. We can get the other two coordinates from the first and the first row and the last column, and this is valid as long as the beta angle is not 90 degrees, because when beta is 90, the cosinus of beta is 0, and then we cannot obtain or we cannot use this expression. Okay. As you can see, in this case, for alpha and gamma, we obtain them from the corresponding elements as indicated in the expressions by doing an arctangent of the division of two elements of the rotation matrix. So when beta is 90 degrees, this actually corresponds to a gimbal lock situation, and indeed we lose a degree of freedom. We can easily see this by just simply substituting beta with 90 degrees and applying after some maths. We can obtain the analytic expression of the resulting rotation matrix, and we can see indeed that alpha and gamma contribute both of them to the same direction, or to the same contribute to the same rotation in this case. So we can obtain multiple combinations of alpha and gamma to represent the same orientation. To end this presentation, I just simply would like to indicate that there's a good URL to convert 3D rotations to different representations, and this could be handy in certain situations. So just write down the URL, type it on your browser, and you can practice with it. So to summarize, in this video, we have introduced Euler angles and its relation with rotation matrices. Thank you very much.